for the Industrial Electronics in 4 module. So this is the second part, which yesterday we did the first part. Now today is going to be the second part. If you want to get the video from yesterday's lesson, it's going to be loaded into my class today so that you can just go through it. It's going to be loaded in week 6, and you're going to see it there, and then you can basically go through it. So what we are going to be covering is the semiconductor part 2. Yesterday I went through the scope. I will just go through the scope at the end of this lesson so that you know what you need to study for the national test, which is going to be on the 15th. Okay, so the 15th of this month, 15th of February, sorry, until the 19th of February is going to be the national test. So today we're just going to go on the second part and learn more about semiconductor. Now, the semiconductors, we covered all the basic ones. So now we're going to look up at the different types of semiconductors we have. So we're going to look at the Zener diode and the application of the Zener diode. So the Zener diode is basically is used for regulations, but it's basically a referred voltage component. The Zener diode can be used instead of an original diode, provided that the reverse bias voltage is always lower than the Zener reference voltage. The Zener diode is basically used mostly on the reverse bias section because its forward bias is just like the ideal diode, but in the reverse bias, it's more different. The symbol for the Zener diode you can see on the screen on your right-hand side, left-hand side, sorry. You basically have the two symbols you can use to represent the Zener diode in a circuit. The one has a Z and the one that just has a like an L shape representing on the cathode side. Then we have a characteristic curve, which is very important. One of the things that you should know, how to draw the characteristic curve for the Zener diode. So we have forward bias is just the same as that of an ideal diode, but when it comes to reverse bias, we have the breakdown Zener voltage representing the knee, in which the characteristic curve it changes direction and starts to conduct in the reverse bias. Then we have the IZ, which is the maximum Zener current, and we have IZ minimum, which is the minimum current produced by the Zener diode. Okay, it's a silicon junction diode that is especially doped to obtain its unique characteristic. It's doped in a way, like we talked yesterday about doping and what is the purpose of it. We said that doping basically is used to change the characteristic of a semiconductor material. It's made to make sure that the semiconductor material becomes more like a p-type and an n-type, so that we can put them together and have a p-n and have a diode. Okay, so we talked about what doping is, the process of doping, and how to make an n-type and how to make a p-type. Now, with the Zener diode, they do a specific unique doping that is not the same as the ideal doping to make sure we have the Zener diode. Okay. It will not break down in reverse bias condition like the ideal one if it is used within the limit of its specific. So it's basically the limit of a specific is between 0 and that of the Zener breakdown region. Okay, it will maintain a steady voltage across the diode and in the reverse bias condition of the Zener diode. It behaves like an ordinary junction diode in forward bias condition, and that is one of the things we need to know. These are all characteristics of the Zener diode that is important that you need to know. So when they ask you questions on list the characteristics, you should be able to list them. So from the slide, you can see all of this stuff. Any questions so far before I go to the next slide?
Yes, ma'am.
Yes. What's your question?
Yes, ma'am. This Zener diode, doesn't
Yes.
it look similar than the N3 when it's the semiconductor diode?
Yeah, it is the same, almost like this normal diode. The only difference is that it's like a Z we have there representing, yeah, at the front.
All right, ma'am.
Yeah. So the other thing you should know is like if you compare them between the ideal diode and the Zener diode, is that they do have the same forward bias function. They work the same. So if you had it in forward bias, they act like a closed switch. But the difference is that it's the way they work in reverse bias that is different. Okay, that is what's difference between the two. Okay. So the next one is, we're still talking about Zener diode because there's a lot to know about the Zener diode. As you can see, when the Zener diode voltage is exceeded, the avalanche point, which is the spot here where it starts to knee over. So you see, we're looking at the reverse bias part. You see when it's going straight and then it gets to the VZ, negative VZ, and then it starts to knee. That's the avalanche point. It will be reached and the diode will be destroyed if you basically go over this value of that VZ and you apply more power than it's supposed to be applied to the Zener diode, you will burn out your Zener diode, and they do explode. They do have a popping sound as if they just like blew up. So your voltage has to be between this one here. The negative, there's no such thing as negative voltage, it's just the way in which you connect it. Okay, so remember, so that will be you putting the negative polarities of this battery to the anode, and you put in the positive to, sorry, saying the negative you're putting to the anode and the positive you're putting at the cathode. That's why that's how we get the negative voltage. It's not about negative voltage supply, it's about the way you connect it that gives us the negative sign. Okay. So what you should know about the Zener diode, you cannot exceed the Zener voltage. If you reach that point where we have this avalanche, then you will have a damaged Zener diode and it will not work anymore. Okay. A small reverse current flow in the reverse bias condition before the Zener diode reference value is reached. So we have reserved current. Basically, reserve current is very small. You cannot see it. It sometimes looks as if the component is not even working, almost as if the component is an open switch because there's like so little that can be read there. And sometimes you notice when you are measuring with the multimeter, it almost gives you a zero value, but there is current there, but it's just little. In the Zener area, a relatively large current flows through the diode, but if the current is kept within the limit of the diode, it will not destroy itself. So you have to keep it between this avalanche. Sorry, I'm going to mute you. Sorry about that because your mic is interrupting. Okay, thank you. Now, the other thing about the Zener diode is the application of the Zener diode, which is one thing you should know. The Zener diode is basically used as a reference. It's used to regulate voltage. It's a regulator. One of the things you guys didn't do so much in the power supply, but you should know that it basically cuts down voltage and makes it into a direct value. Let's say you're getting an input that is going up and down between 5 and 0, 5 and 0, and 5 and 0. And you want the output, the load resistor here, to only use 5 volts. So the Zener diode will make sure that this unregulated input becomes stable. So we have a stable output coming into the load. That is what the main purpose of the Zener diode is. It's just to make sure that we have regulated output. It's used in the power supply at the last step, which you guys didn't really cover, but it's used on the last step because when a power comes out of the filter, the second filter, it is filtered out and the signal is a little bit better. It becomes more like a DC, but we still have that bump. And that bump is something that we don't want. We want it to be straight. So we use a Zener diode to just smooth out the signal so we can have a straight value coming out into the load. Okay, so the Zener diode is used for as a voltage regulator, and it can also be used as a voltage reference, which it means that it refers, it takes the value that is coming in as unregulated value and refers it to the referred value. So it can be basically used like, what I mean is that the Zener diode itself has a reference value, and it compares that value to the value that is coming in. And if that value is not, it will not allow the output, it will not allow output to come out. But if it is, it will allow for the output to come out. Where it is used for a voltage regulator, it makes sure that we have a stable output at all times. So it gives you an output even though we don't have regulated value coming in. But as a reference, it makes sure only the right value comes out. Okay, if you understand that. Okay, so this is an example of how we use the Zener diode as a voltage regulator. So this is an example you could get from a test. So please make sure you make note of this because this comes out usually in a test. Okay, 5 volts stabilized power supply is required to be produced from a 12 volts DC power supply input source. So our input is 12 volts, and they want an output of 5 volts to come out of the regulator. Okay, so they say the maximum power rating, which is the Zener power rating. Very important to know, every Zener has a different power rating. So when you buy it, you get it a characteristic, basically a data sheet that tells you every information you need to know about the Zener or the diode you buy. It tells you how much power you're allowed to use. If you exceed that, you'll damage it. It also tells you how much voltage you're allowed to use. If you exceed that, you damage it. So they tell us the maximum power rating is of the Zener diode is 2 watts. So we're not allowed to use more than 2 watts on the Zener diode itself. That's important information when you're calculating regulation. Then they say using the Zener regulator, calculate the above calculation. So we need to find out the maximum current we're allowed to use on that Zener diode in order to make it to work with it as a voltage regulator. So what we know is the current is basically the equation for power is P is equals to V times I. So if we make the current the subject of a formula, we're going to have this formula that is on the screen. This maximum current is equals to watts divided by the voltage. And that's why we get 2 watts divided by 5 volts, giving us 400 milliamps. Okay, that 400 milliamps is the maximum current that the Zener diode can have in going through it to prevent it from getting damaged. So if we have more than that going through it, we're going to damage our Zener diode. So now the second question is like the minimum value of the series resistor. So if you're going to use the minimum value of a series resistor, you basically need to find out what value the series resistor has to be in order to not get damaged. Because you can see from this diagram here, this R here that stands here before the Zener diode that's in series. This is the series resistor. This series resistor drops the voltage before it gets to the Zener diode. It's a protective measure, okay? It has to be a right value to make sure that the voltage that goes to the Zener diode is exactly the amount the Zener diode needs, or else it can cause the Zener diode to get damaged. So we have to find the maximum power the Zener diode can use so that we can find out the exact value this resistor has to be so that it can take down any voltage drop or eliminate any current that could go in there and damage the Zener diode. Okay, so you need to understand that the series resistor causes a voltage drop at protecting the Zener diode. So that's why we work it out. So the minimum value of the series resistors R is equals to Vs, which is the voltage in series or the voltage supply, minus VZ. VZ standing for the Zener diode voltage, which is the referred voltage. So the referred voltage they told us is 5 volts. It has to supply 5 volts. So that Zener diode voltage has to be 5 volts. So the supply is 12. So it's 12 minus 5. That will give us the voltage going through the parallel. Divided by this will give us the voltage going through the series, sorry, divided by IZ, which is the maximum current going through the Zener diode, gives us the value of 17.5 volts. So this series resistor you see in this diagram will be 17.5 ohms. It has to be 17.5 ohms in order to protect the Zener diode. Okay. Okay, the next question says to calculate the load current, the current going through the load IL, if the load resistor is 1 kilo ohms, is connected across the Zener diode. So we have the Zener voltage, which is 5 volts. That is important. We have to understand if we're working out the current going through the load. Okay, the current going through the load. You know that in parallel, because this part of the circuit is series and then it becomes parallel. In parallel, the voltages are the same. The current splits. So if we want to find out I2 or the IL, the current going through this part here, we have the value of the resistor and we have the voltage of the Zener, which is the same which is gonna be the same voltage going through RL. Yes?
Ma'am, when you said the resistor in parallel, why did you say the voltage is the same?
Yes, because the rule is that when we have in parallel, the voltages are the same. The current is the part that splits because there's two paths. So the voltages remains the same. In series,
Uh,
the voltages split.
Okay, ma'am.
Okay. Did I answer you? You understand?
Yes, ma'am.
Okay, that's good. Okay. So what happens is that we do now have the voltage going through. RL will be the same as the voltage going through the Zener because it's the parallel rule. We have to use that as a source of information of how we're going to get this answer. So the answer there will be IL is equal to VZ because it's the same as the voltage going through the resistor divided by RL, 5 divided by 1,000, which is 1k ohms. Okay, so it's times 10 to the power of 3 is equals to 5 milliamps. Remember, the Zener diode voltage has to be 5 because they say they want a 5 volt stabilized power supply. So the voltage regulator stabilizes voltage. So if they tell you that, that means that that's what they want the Zener voltage to be. Okay, so you must make sure of that. Guys, this question here is as far as they can go with asking a question about the Zener diode. They sometimes like you to answer questions like, what is the value of the resistor supposed to be? They like to ask you sometimes they like to ask you what the value of the resistor could be. There's not much questions they can ask with this question. It's almost the same type of questions. Okay, there's one more question that they ask. They asked for the Zener current, which is another question that is similar. This Zener current, you can see this Zener current is the current going through here. I told you the current splits when it comes to parallel. At this point, the current goes there and there. Remember Kirchhoff's current law. The current goes through different ways. The same current that comes in is equal to the current coming out. So it means that I1 is the sum of the voltage going through IZ and I2. That's how we get I1. So if we have the value of this resistor and we have the series values, we can find I1. If we have the value of the current going through the load, we can actually find the value of IZ. So you can see what they did here is basically they went straight to it. They didn't do what I did. They went straight to it because they have the value of the maximum Zener voltage. I mean, they have the maximum value of the current in a series minus the value of the current in the load. Yes.
Ma'am, doesn't it look
Yes.
similar? Ma'am, doesn't it look similar like in Kirchhoff's current law when the total current flowing towards a junction equals to the current moving away from that junction?
Yes, it's the same. It's the same rule. They use that rule there. It's the same
Okay,
rule.
ma'am.
Yeah, you see that the equation here is Iz is equals to Is minus IL because we are trying to find this current here. So this current, to get this current, it will have this, which is going in this direction in, minus that one which is going the opposite direction. That's how they got Iz. Makes
Okay,
sense?
ma'am. Yes,
Yeah.
ma'am.
So that's how they got that value there. They got the value of Is and then they got minus it by IL. Let me just see if they did calculations on Is, Is, Iz. That's the maximum value. Okay, no, they didn't do a calculation for Is. But if it's to do calculation for Is, this is how you do it. I'm gonna show you. The Is is gonna be equal to Vs minus, please write that down. Is is going to be equal to Vs minus Vz or VL divided by, you got that? Is 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 equals to Vs minus Vz divided by Rs. And they'll give you the value of Is, which is going to be 400. Do you understand? They didn't do it there, so I'm just telling you how you're going to get that value. For 5 milliamps, they did it in the previous exercise, so that's how you got that value there. And that's how we got the answer of 395 milliamperes. Okay, so what I will be expecting you to do is go through the activities on my class at week 6 in order to see if you can find a question on the voltage regulator, because there are questions there on my class week 6. Okay. Now, the other diodes we find in semiconductors, the Veritas diode, which actually is symbolized like that because it uses a capacitor as the PN junction. That is what is different of this diode to the other diodes. It uses a capacitance. So we have two characteristic curves, and sometimes they ask you in a question, draw the characteristic curves of this diode, and then they expect you to know that you need to either do this one or that one. This one here is just the same. I think the first one, A is the voltage and current characteristic curve. Is the same as the ideal one, but you must understand that this Verita diode, they call it Verita diode. I'll just explain that. This Verita diode has capacitance, so you have to also draw a characteristic curve with the capacitance. So as we increase our capacitance, we will basically increase the voltage. So we have a capacitance voltage, a characteristic curve, which is at the B there. Okay. It's called Varictor diode because it's basically short for variable capacitor diode. So sometimes if you look it up, they call it variable capacitor diode. It's the same diode, okay? So it always is basically used in the reverse bias condition. Most of these diodes are used in reverse, but the ideal diode is used in the forward. So this one here is used in the reverse bias condition, and the capacitor is at its smallest during the reverse bias condition. And reverse bias causes the duplication region to increase, and thus decreases the the capacitance. So remember capacitance, there's three things that affects the capacitance, and one of them is the distance between the plates. The further the plate is, the the further the plate is, the less capacitance. The closer the plate is, the more capacitance it is. So as you see there, if we are in a reverse region, the duplication region increases like it should in reverse bias, and therefore that decreases the capacitance, which is important to allow for the for any function to happen. The more capacitance it is, it's harder to function. So in a way, it doesn't work properly in the forward bias, but it will work better in the reverse bias because of the distance between the plates. So the characteristic curves follow the exponential mathematic curves, and it's not linear, as you can see in the B here, the B diagram here. This one is what it looks like with the voltage and current one, voltage and current characteristic curve, but this is the voltage and capacitance characteristic curve. You can see in reverse bias mode, the capacitance is low, and in forward bias mode, we have a huge amount of capacitance going through the two types of material, the PN. Okay, so that's what we know about the variable. It's not really much. So that's the only, you need to know about the characteristic, and we need to know the diagrams. We don't need to know very much about what it is. And the other thing you need to know is the application. So I will suggest you look it up. I'll try to see if I can find the notes now here. Now the tunnel diode, as you can see here, there's a symbol for it. And the characteristic curves looks like this. It has like a tunneling current there. This diode is highly conductive in a reverse bias. Most of them work in reverse bias, as I said. It is made out of silicon, germanium, all this material listed here are semiconductors, okay? So they all work differently. In forward bias condition, it basically conducts immediately and starts at a breakpoint, and then with an increase in the forward bias, the current drops to the valley point, where after it follows the curve of a normal diode. So at this point, this is the only difference it has between ideal diodes and this tunnel diode. At the forwards section, it will increase immediately, conducting immediately, acting like a closed switch, and then it closes down, giving us negative resistance, basically closing down like a tunnel. It's closing down. When I mean like a tunnel, I mean that electrons are supposed to flow through the p-n junction. So at this point here, this is like the tunnel is opening up. There's a big tunnel, and is allowing for a lot of electrons to flow. As soon as it gets to the B point here, where it goes down, the tunnel closes up, and it restricts the amount of current going through, or electrons going through, and then it starts to work as if it is a normal ideal diode. So that's the only part that is very different from all the other diode. Okay, is there any questions? Okay, so I just want to go through the syllabus of what you need to know for national test, so that because you weren't here yesterday, so I just give you a rundown of the syllabus of what you need to cover for the national test. Okay, I'm not sure if you can see it. Okay, I can see it now on my side. I'm not sure if you can see it yourself. This was from yesterday's class, so I'm just going to cover what you guys need to know. These are subjects that you need to know, that you need to cover for the national test. The date of the national test is between the 15th and the 19th of February. So the subtopics you need to cover is direct current theory, case, and that is basically the uh, calculations of power and network theorem like Kirchhoff law, superposition, and Thevenin. And then the other topic that's going to be covered is alternative current theory, which is week 3 content. It's week 3 content on my class. So I'm just giving you the weeks. Direct current is week 1 and 2 on my class. Alternative current is week 3. You will find the content there. You will find some notes, and you will find PowerPoint and videos and exercises which you need to go through. So alternative current theorem, you will find phase diagrams, simple complex calculations. That's alternative. You need to know how to do the complex calculations with circuits and the phase angles and stuff, as I've repeated it here. Then week 4 is the last week. Week 4 is not the last week, it's the week before. It's the same as alternative current. You just have to find out how to do a characteristic curve of the Q factor, the bandwidth, the maximum power transfer, and you also need to know about the resonance frequency in series and in parallel. And then week 5 is the last week of that national test. You need to know how to do most of this stuff here. You need to calculate the forward and reverse saturation current. I did that yesterday. Okay, so you need to basically, the content of this is in my class week 5. You will find the calculations for ideal and the one for non-ideal. So you need to know that, how to do that. You also need to know how to calculate, do the calculations of the voltage regulators, which I just did now. And you need to know the properties and the characteristic curve and application of tunnel, variable, and the Zener diode. So those are the contents you need to cover for national test, which will be between the 15th and the 19th of February. So it's going to be soon, guys. You need to prepare. Is there any questions, guys?
Yes, ma'am. I'd just like to ask.
Mm-hmm. Yes.
Okay. So what's happening at this point is the first test will start in February.
Yes.
Do you know when is the and what happens on the second test then the exam? Will it be the second test on March or the exam and the exam on April?
Yeah, I believe you guys they're gonna write out April, I think. Let me just check our email. Okay, sorry about that. Let me check my email. I have this. I was sent an email on this stuff. Okay, you are writing the DP exam on the 15th of March to the 19th, from the 19th of February to the 15th of, sorry, the 15th of March to the 19th of March. And then you're gonna write in April.
Okay, ma'am.
Okay, so that's gonna help. So you're gonna write your DHET in April. By March, you should be finished with the national test and the DP.
And one final thing, ma'am. What happens though, ma'am? Like what happens, ma'am, if you fail? If we get our reports, okay?
Yes, and
Um,
you
if
from
you
the
yes from last semester, if you feel like, for example, one topic, do you do
you
we
have
still
to
have to?
You have to go back and do the subjects. You know, if you have already qualified to write the exam from last semester, but you failed it, that means that you need to only for the DHET, which is on April, you have to write that subject you failed. Do you understand? But you can still write the test for this semester.
Oh, and for the DHET exam for rewrite,
Yeah.
do we have to pass for a percentage of 40%?
For rewrite, you can rewrite even if you fail. So what I'm saying is that if you failed last semester, you failed this subject on the DHET, but you did get a DP, you can write it on the April. Again, you rewrite it. But if you failed the whole module, you never got a DP, you have to do the subject again and then get a new DP. So that means on this 15, you're not going to write the subject, you have to write the one that you failed if you didn't get DP. Does that make sense?
What is a DP, ma'am?
The DP mark is the one you get 40% of your term mark. So it's national test and the DP test, the two tests that you wrote. If they combine it together, you have to have a percentage of 40% to qualify for government exam. So if you
Oh,
did not get that 40%, you have to do the subject again from beginning.
okay, do it from the
Yeah.
beginning.
You have to write on the 15, uh, you have to write the national test from the subject you failed.
Okay,
Yeah, if you didn't get DP. But if you got to a point where last year you actually sat down for the government exam, the DHED with the permit and everything, that means you did get a DP and you're only going to write that subject again on April if you failed it previously.
I understand,
That's,
ma'am.
yeah, okay. So that's what's going to happen. Any other question, guys? You good?
I'm good,
So
ma'am.
okay, good. So today I did semiconductors. I finished with semiconductors. The previous video will be loaded so you can see that video and this video so you can summarize the notes and go through it yourself and exercise and do some work. And next week I will be covering a bit about AC again and I won't do so much on it because now I need to start covering stuff for the next test, but I wanted to go through a revision classes. So that's why I'm doing this again. So if you weren't here in the beginning from last semester, you can just go through these classes that I put online. Okay. Thank you guys so much for coming to the class. I hope to see you next week, Tuesday, same time at 11 o'clock. I will be putting the link on the week 8 so you can see it there.
Okay, thank you, ma'am.
Okay, thank you. Thank you. Bye.
Bye, ma'am.
Bye, man.